Hello, everybody, and welcome to our very last AP Calculus session. We will be working through some BC material today. We're going to add in a little bit more differential equation work. That is the end of Unit 7. And then we're going to do some sequences and series work, which is the kind of part of Unit 10. We will not cover all of Unit 10 because parts of this are off of the curriculum for this year's AP test, but we will do some of the pieces of Unit 10. So here is where we are going today. We are going to, again, start with two quick Unit 7 differential equation pieces, and then we will turn to that sequences and series work. We're going to very briefly talk about convergence and divergence, a little bit with recognition of geometric, harmonic, and P-series, and then really dive into using the alternating series test and the ratio test, as well as finding approximations using Taylor polynomials. In our last session, our AP-BC combo unit session, last Wednesday, we talked about using separation of variables in order to solve a differential equation for both a general solution and a particular solution if we were given an initial condition. And we finished this by looking at one particular model that has a hopefully fairly recognizable form. So we ended with this exponential model idea here. And even if we use separation of variables or separable variables to go from this starting knowledge to this actual function, we can get ourselves there using math. But again, we do want to be able to recognize this exponential model situation just kind of right away when we know that the derivative or the rate of change of a function is proportional to the actual function. Hopefully we can recognize that this is an exponential model. And again, just like we talked about last session, this is very common with population. There is one other specific model that we call out and name in the AP Calculus curriculum, and that is the logistic model. The logistic model is a manipulation of the exponential model that introduces a maximum capacity. So this letter that you see here, this M, is called our maximum capacity. And what is happening here is that we're taking something like population. So let's continue to work with this idea that P is the population or a population. We're taking this idea of population, we're saying that it's going to start out growing at an exponential rate. It's going to start out kind of looking like an exponential function, but eventually it will hit a point where it will stop growing exponentially. It'll hit a capacity and then start to kind of level out. So what this really means is that the relative rate of growth, so that derivative idea, that relative rate of growth will actually decrease as the population approaches M, its capacity. And then if the population were to surpass M, that relative rate of growth will actually become negative. This type of rate of change, again, looks like this. So it almost looks like we have this exponential start. We have this rate of change that is proportional to the population. And when the population is really small, this P over M is essentially 0. When the population is really small, this does look exponential. But once that population starts growing, again, this rate of change is going to start decreasing. We can follow separation of variables here as well. We can take this and do all of our integration work that we talked about in the last session, and we will get to the actual function. It's a lot more complicated than just the exponential model that we looked at in the last slide. The separation of variables involves partial fractions in the integration. It is great practice if you want to review partial fractions. But once we do that, we would end up with this function here, where we still see M, we still have our capacity, and we also have another constant, this letter C, where this is working just like we looked at in the last session in that exponential model. This is working as e to some constant we're rewriting as just its own constant. So hopefully you can look at this function and see that this is a manipulation of an exponential function, but it kind of has a limiting factor, or that capacity. These were very uncommon type of questions on an AP exam. They were generally multiple choice questions that just involved recognition of this differential equation, such as which of the following differential equations represents a logistic differential equation. So just make sure that this is somewhere on your list of formulas, the list of things to be able to recognize, but you shouldn't have to really dive in much more than that. Again, this is great integration with partial fractions practice, but make sure that at the bare minimum, you can recognize that this differential equation here, this dp over dt equals kp times 1 minus p over m, represents a logistic differential equation where p is that population and m is the capacity. Okay, now we're going to dive into some actual algebra here. So we have one approximation method that is associated with the differential equations in Unit 7, and that is Euler's method. And Euler's method is very similar to the idea of local linearity that we talked about in the very beginning of our review of calculus. So for instance, if we have a function that looks like this, let's say we have a piece of a quadratic looking function, and we build a tangent line to this point right here. Let's see if I can do this. So we create this tangent line. If we zoom in really, really, really closely, we can use that tangent line to make approximations for our function values at values that are really, x values that are really close to that point of tangency. So maybe this piece of the line right here. Because right there in this area, this teal area that I'm highlighting, our tangent line and our actual function look pretty similar. So I'm getting ahead of myself here. Euler's method is very similar. And it's essentially this idea of local linearity of using a tangent line to approximate a value, but stopping every so often and changing the tangent line, changing the slope, changing the direction of our approximation. In a formula sense, that looks like this. So let's say that we start at f of 0. And then we start moving from f of 0 using the derivative at 0, using the slope of the tangent line at 0. And we do that for a distance of 1/2. That would give us an approximation for f of 1/2. But then at this new point, f of 1/2, this new approximation, we're no longer going to use the derivative at 0. We're going to stop and use a new derivative. We're going to stop and use a new direction, a new slope of a tangent line evaluated at 1/2. So now we're at 1/2, and we are going to reevaluate our derivative at 1/2, use that for a distance of 1/2, and that will take us to an approximation of 1. And then we are at 1. We are going to reevaluate our derivative at 1. We will use that for a step of 1/2. And that will give us an approximation for 3/2, and so on and so on and so on. And the really important parts of this, of using Euler's method, is some known information from our question. Our question would have to tell us where we're starting and where we're trying to go. We want to know what that ultimate approximation is that we are working on. And then also the step that we will be using. I just made, double red here. I made up this 1/2 step in this particular case. It could be anything. It could be given to you, or we could be told something like start at 0, do an approximation for f of 1 and use 3, that would be a bad example, use 4 equal steps or use 2 equal steps or some situation like that. So we do need to know in a Euler's approximation method, we need to know where we're starting and we need to know what our step size will be. How long will we be working off of the same slope of a tangent line before we stop and reevaluate and change direction? So let's go ahead and get a question that uses that idea. And this is a question from the 2016 exam. It actually walks through almost everything that we have done in calculus up until this point, with the exception of maybe 2 or 3 topics. So we're going to use this as kind of a warm-up today, walk through some ideas, and then end it, part D, end this with Euler's method for an approximation. So here we have a differential equation. Consider the differential equation above. Notice right away that this is not a differential equation that looks like it's going to lead to an exponential model or a logistic model. It's just something else. And our first question here, our first part here, is to find the second derivative in terms of x and y. Nothing to do with anything in Unit 7. This is a review from the very beginning of calculus. So if we are finding a second derivative, the second derivative of y with respect to x, first of all, just quickly make note of that notation. Those 2's are not vertically aligned with each other. Just be careful of that when you are going through your work. And we are differentiating with respect to x, which will mean that we need to pull in some implicit differentiation anytime that we are not differentiating x. So here we have that is not a pen, hold on. 2x minus 1/2 dy over dx. That is not the end of this part of the question, because it says to give the second derivative in terms of x and y. That means x and y should be the only variables that we see. So we need to do a substitution and put all of this here. Let's move that so I can actually see everything at one time. All right, so my second derivative will look like this: 2x minus 1/2 times x squared minus 1/2 y. I'm going to go ahead and distribute that 1/2 as I'm doing this, just because the calculations in the parts below will be a little bit easier. So there is our second derivative. There's our final answer for part 1. Now let's look at part 2 here. Let y equals f of x be the particular solution to the given differential equation whose graph passes through the point -2, 8. Does the graph of f have a relative maximum, relative minimum, or neither at this point? Justify your answer. So this part looks like a setup for a differential equations question to start, but actually goes back into that graphical analysis of the relationship between a function and its derivatives, which is not at all a Unit 7 question, but is a great review here. So we don't have the ability to actually get ourselves to the function. This is not a separable variables type differential equation. We really can only work with the 2 derivatives that we have on screen right now, the first derivative and the second derivative. So we can figure out this relative maximum, relative minimum, neither situation by figuring out what the first derivative equals at this point and what the second derivative equals at this point. And I just want to remind you of some quick notation, and then we can move on from that. So the first derivative, I want to evaluate it at the point -2, 8, which we can write like this. This means evaluate the derivative at this particular point. And when we do that, I will spare you all of these calculations. When we do that, we get 0, which is great. That's exactly what we wanted to get in this case, because we know that at a relative maximum or a relative minimum, our derivative would be 0. But that is not enough to actually answer the question yet, because we would now be in 3 situations. At a maximum point, so here's our potential -2, 8, we do have a derivative of 0. At a minimum point, we have a derivative of 0, but we also have a derivative of 0 at a point like this. And right now, -2, 8 could be any of those. The difference between these 3 points, or these 3 situations, is that the second derivative is different in all of these cases. Here, the second derivative would be negative, our function is concave down. Here, our second derivative would be positive, our function is concave up. And here, our second derivative would be 0, our function is changing concavity. That point -2, 8 is a point of inflection. So we are going to go do the same thing here. Nope, not that. We are going to do the second derivative and evaluate that at the point -2, 8. And when we do that, we're going right to this function that we calculated, -2 in for x, 8 in for y. And in that case, we will get -4. So pulling all of this information together puts us in this situation, negative second derivative. So our function at this particular point is concave down, and our first derivative is 0. So we do have that horizontal tangent line. That gives us a relative maximum. And we would want to formalize that for this part in a sentence, an English sentence, a mathematical sentence, whatever we want it to be, where we pull together this information and say that because the first derivative is equal to 0 at the point -2, 8, and because the second derivative is equal to -4 or is less than 0 at the point -2, 8, we have a relative maximum. So there was a review of a lot of calculus so far. Let's do a little bit more. So part C, or the third part of this question, let y equal g of x be the particular solution to the given differential equation with g of -1 equal to 2. Find this particular limit. Now we're all the way back into the beginning of calculus again, still in a frame of a differential equations question, a frame of a Unit 7 question. We are now being asked to review an entire other section of calculus again. So now I know that this differential equation represents the derivative of g of x. So I can think about that as I'm actually working through this limit question. And I'm going to mostly talk through this one and then let you work calculations later as you want to. Remember that when we have limits, I just want to remind you of some notation. When we have limits like this, what's really happening is that we are separating this limit into the limit of g of x, the limit as x approaches -1 of g of x, minus the limit as x approaches -1 of 2, all divided by the limit as x approaches -1 of that denominator, which is this. And when we evaluate that, what happens here, when we do this evaluation, I know that this is the part that we have to pull from the question. This limit as x approaches -1 of g of x is equal to 2. We know that this function is continuous because it is differentiable. And when we do this, we get 0 over 0, which is indeterminate, which means that we can apply L'Hopital's rule and do this whole limit again after we take the derivative of the numerator and the denominator. When we do that, we are going to have to evaluate the limit as x approaches -1 of g prime of x, which we would do here. When we get to that point, we also get 0 over 0. We get 0 over 0 again. We get an indeterminate form again. So we apply L'Hopital's rule a second time and end up having to evaluate the limit as x approaches -1 of g prime of x, which would force us back to our second derivative to evaluate this at the point -1, 2. And once we do all of that, that will finally give us something that's not indeterminate form. And once we do all of that, we will end up with this limit equal to -1 over 3. So this one is some good practice for using L'Hopital's rule. So again, so far we've hit implicit differentiation, connection between graphs of functions and their derivatives, and L'Hopital's rule with evaluation of limits all in one free response question. And now we are finally getting to the differential equations part. So let y equals h of x be the particular solution to the given differential equation with h of 0 equal to 2. Use Euler's method starting at x equals 0 with 2 steps of equal size to approximate h of 1. So then we know that this, in now this situation, part D, this represents my derivative of h. So here's our information that we need. We need to start at 0. We need to get to 1 with 2 steps. So that means our step size is 1/2, just like the example that we did in the very beginning. So that means that I'm going to start at 0. I am going to use a step of 1/2 with the derivative evaluated at 0. And I am going to then get an approximation for h of 1/2. Then I will be at h of 1/2. I will use a step size of 1/2 with the derivative evaluated at 1/2. And that will lead me to an approximation for 1. Now, this is a lot of plugging in numbers, of doing that math to substitute in particular values of x and y in this derivative in order to get these. When you are doing that, you need an x value and a y value. So think about that x value here with its associated y values. So when x equals 0, y equals 2. When x equals 1/2, y equals something that we have not yet figured out. So a lot of substituting in numbers, a lot of just, here's my x value, here's my y value, I'm going to evaluate. Once we do that, I'm going to do some of that here. Once we do that, we end up with this. So h of 0 is equal to 2, that's given in the question. And h prime of 0 is equal to -1. Let's move this one over here. Which means that h of 1/2 is approximately 3/2. So there's our next point that we can actually use in the next calculation. 1/2, 3/2. When x is 1/2, y is 3/2. Then we're moving over to here. And h of 1/2, we just approximated that as 3/2 plus 1/2. When we evaluate the derivative, this differential equation given to us at the top, at x equals 1/2, y equals 3/2, we end up with -1/2, which is going to give us 3/2 minus 1/4. So 6/4 minus 1/4, 5/4. And that's our final answer here. Our approximation for h of 1 is equal to 5/4. Okay, now we're going to dive into Unit 10. Unit 10. Unit 10 is complicated, to say the least, and it is so deeply based in theory and various proofs that I am going to not really talk about most of it because I can't do it justice in only a few minutes. Instead, we're going to really just look at the most basic underlying concept and then at the rules and execution of the various tests that you're responsible for this year, without doing what I typically emphasize, which is to really dive into the why and the proof and the making connections between ideas. And again, that's just because if I start with that anywhere in these next few slides, we're really committing to a good 5 more hours of this section here. So here's what we're looking at. We have a series. So the sum of an ordered list of numbers. We have a series, and that series is made up of terms. So once I start writing out my series, it's made up of terms. When we add, that's a double purple there. When we add the terms together, we get a sum. A sub 1 plus blah, 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 all the way to a sub n equals something. If that sum exists and is a real number as we let n approach infinity, then we say that our series is convergent. If that sum either does not exist, is not a real number, it's infinity, negative infinity, something not nice and beautiful, then we say that our series is divergent or diverges. So that is the most basic underlying 1-minute version that I can give you to kind of concentrate on as we go through the next couple of slides. So there are several special types of series that we study in calculus, and several, actually probably way more than several, tests for convergence that we use in calculus. This year, we need to be comfortable with 3 particular types of series and 2 particular tests for convergence. And the 3 series that we need to be comfortable with are geometric series, harmonic series, and p-series. So a very quick overview, again, not really any proofs or deep explorations as to the whys of things, but just a quick overview. First one, geometric series, which hopefully is still something in our brains from Algebra 2, pre-calc, some kind of connection to exponential growth and exponential decay here. A geometric series has a common ratio. So R is the most important number or idea of a geometric series. Something like 2, 4, 8, 16, 32, 64, where that R, that ratio is 2. A geometric series converges if R is less than 1, and it diverges if R is greater than 1. Nice and simple. We have one condition, really, 2 different steps of that condition, and then we know everything that we need to know about the convergence or divergence of a geometric series. So for a geometric series, we need to be able to figure out what R is, and then we are going to be in one of these situations. A harmonic series is just the series from n equals 1 to infinity of 1 over n. And there are no real conditions here. If we are talking about a harmonic series, it diverges always. It diverges always, and this is one particular series that I just want to quickly look at to talk about one of the most common misconceptions of this sequences and series idea. If we look at this connection to a function, so if we think about 1 over n is the series here, but if I think about the corresponding function of 1 over x, that looks like this. And if I kind of break it off at 1, so I'm looking at this situation here, that looks like, as we are just taking x further and further and further towards infinity, it looks like that our function value is going to approach 0. It looks like we actually are going to be able to find some definite area under this curve. The limit, let me change my letters actually, the limit as x approaches not 0, let me change my letters and my numbers. The limit as x approaches infinity of 1 over x does equal 0. That does not mean that a series is convergent. So again, I just said that I'm not going to go back into a ton of theory, but I do want to emphasize this point because there is a theorem throughout this unit that is often spun around and doesn't work that way. If we know that a series is convergent, then the limit as n approaches infinity of a sub n does equal 0. But just because this type of limit here equals 0 does not mean that the series converges. So if we have convergence, limit as n approaches infinity does equal 0. Just because the limit equals 0 does not mean that we have convergence. And a harmonic series is a really great example of that. Okay, that's the end of our theory. P-series is the other type of series to recognize, and that is a series where we have an exponent to our n. I'm using n for all of these. It doesn't have to be n, but just quickly pay attention when you are writing these down or kind of making lists and thinking through these. Just check to make sure that these variables are the same. These letters are the same. P is not that variable. P is the exponent to n. And we have one thing to check here, one condition with kind of 2 steps again. If P is greater than 1, this series will converge. If P is less than or equal to 1, then this series will diverge. If P is exactly 1, we're right back in this situation here. So those are the 3 series that you need to be comfortable with recognition, with these conditions, with just kind of what they are. These are the 3 particular series for recognition. Now, in a typical year, this test for convergence slide would be very full of things. We have an integral test, a comparison test, a limit comparison test, alternating series test, ratio test, root test, among others. There's a lot of different tests for convergence. They all have their own conditions. They have their own kind of series they work well for. They have their own rules. There's a lot to really work with here. This year, we are only working on 2 of them. We are going to work on the alternating series test and the ratio test. So we are not even going to think through the rest. We're going to just dive right into the 2 that we need to be really comfortable with. So the alternating series test is first. Alternating series test can be used for an alternating series. Alternating series is a series that when written out has alternating signs of its terms. So a positive term, then a negative term, positive term, negative term, positive term, negative term. And when we're looking at an alternating series, we see this -1. Let me pick a color that you can actually still see. We have this -1 to some power that causes the alternation. And then we explicitly separate the non-alternating piece, just the positive series term. And we call that b sub n in most textbooks, in most cases. We can call it really whatever we want in the rules that I'm showing here, the conditions that I'm showing here. I am pulling out the not alternating part as just b sub n. And the alternating series test has two conditions. If we know that the terms are decreasing, so what that looks like mathematically, we know that b sub n plus 1 is less than b sub n. And we know that the limit as n approaches infinity of b sub n equals 0, then we know that the series is convergent. So if we think about that graphically, if I start at n equals 1, for instance, with a positive term, I have positive, negative, positive, negative, positive, negative, positive, negative, and so on and so on and so on. This is what we want our alternating series to look like. We want every term to be less than the term before it, and we want our final terms, our terms as n approaches infinity, to start approaching 0. So in working with an alternating series test, this second condition is pretty easy to figure out. The first condition is much harder. So I'm going to walk you through one example where I'm going to show you how to do that first part. So let's work with the alternating series. We have from n equals 1 to infinity, -1 to the n plus 1 power times n squared over n cubed plus 1. So in this particular case, if we kind of separate out this alternating piece, b sub n is equal to n squared over n cubed plus 1. Take away the alternating piece, that will give you your b sub n. So I'm going to start with the second condition because it's, again, easier. If the second condition is not true, then there's no point in, or satisfied. If the second condition is not satisfied, there's really no point in trying to figure out the decreasing situation. So let's jump right to this limit as n approaches infinity of n squared over n cubed plus 1. And this does equal 0 because this degree of the polynomial in the denominator is greater than the degree of the polynomial in the numerator. Those are your horizontal asymptote rules from Algebra 2 pre-calc. So that's great. We satisfied that condition. First condition, there are two main ways to test if the terms of this function are decreasing. And the first way is very algebraic. The second way is calculus based. So the first thing that we can do is just set up this inequality. B sub n plus 1 is less than b sub n. And b sub n plus 1 would be n plus 1 squared over n plus 1 cubed plus 1. And then we just have b sub n, which is n squared over n cubed plus 1. And we have to verify that that inequality holds, that that is actually a true statement. And this is incredibly algebra-based. If you like to multiply polynomials and can kind of work through that really quickly, this is not a bad method to do. If that sounds like the worst thing you can possibly imagine, this is not going to be your preferred method. But I'm going to walk through this one just to show you what this looks like. So I'm going to multiply this left side by n cubed plus 1, and then I'm going to multiply the right side by this. Or essentially, I'm going to multiply this entire inequality by the common denominator in order to clear the fractions. And then we're going to run through some algebra. We have n squared plus 2n plus 1 times n cubed plus 1. I'm going to go the whole way through this one first and get n to the 5th plus n squared plus 2n to the 4th plus 2n plus n cubed plus 1. And then over here, I have n squared. I'm going to expand out this n plus 1 cubed. I'm going to use Pascal's triangle to kind of cheat my way through this. If you know your binomial expansion shortcuts, this should be pretty quick and easy. Plus 1, but then I'm adding another one so that it will actually be plus 2. So now my right side looks like this, n to the 5th plus 3n to the 4th plus 3n cubed plus 2n squared. So now we're looking at this inequality here. And we can see that we have n to the 5th on both sides, and that looks like everything. So let's just start combining all of our like terms. I'm going to bring everything over to the left side. So I have 2n to the 4th and 3n to the 4th. That would be negative n to the 4th on the left. I have 3n cubed and n cubed. That will be negative, nope, will be negative 2n cubed. And then I have 2n squared and n squared. So negative n squared plus 2n plus 1. And now I have nothing left on my right side. And if we look at this, hopefully it's by this point, it's fairly obvious to look at. This left side, I'll get a new color here. This is going to be a negative expression if I evaluate this for any value of n that is large, which is what I care about. This truly is negative. This is less than 0. For n greater than, if we want to be really careful, we can say for n greater than 2. Again, we aren't starting our n values until 1. So we can specify some n value of 1 or greater. What you'll often see in this situation, if you go this algebra method, is that you get to a point where this is actually not, let me circle the whole thing. This is actually not a true statement when n equals 1, but as soon as n is greater than 1, it is a true statement, which is why I generally just do this. If it's true for 1, great, you can start there, but be careful with that part. Be careful, actually check when n equals 1. Most cases, or a lot of cases, it's not a true statement when n equals 1. So that's the algebra way. Second option is to evaluate a derivative and see if that derivative at most of our n values is negative, which would mean that the function is decreasing. So that option would look like this. I'm going to do a little bit of that one. For that option, we would take a function that corresponds to our b sub n right here. So let's say x squared over x cubed plus 1. And then we would find its derivative. So our derivative here is going to look like this. Derivative of the numerator times the denominator minus the derivative of the denominator times the numerator over the denominator squared. And that would give us, here we have 2x to the 4th, and then we have 3x to the 4th, so that gives me negative x to the 4th plus 2x. And then I need to figure out the critical points here. I need to know, where does this equal 0? If we're looking at this fraction, we need to set this equal to 0. That means our denominator is not going to affect anything. That denominator can't be 0. And I'm going to factor out an x and kind of flip this around. Say that here's my equation. This means that at x equals 0 or at x equals the cube root of 2, I have my critical points. Because we are looking at values of n that are 1 or greater, positive values of n, we don't really care about this. And we want to then know what's happening when x is greater than the cube root of 3 over 2. We could set up a sign chart. We could go through all of our unit 5 stuff here. Or we could just evaluate our derivative at some value of n that's greater, or x in this case, sorry, some value of x that's greater than 2. If I go back to the prettier version of this, negative x to the fourth plus 2x over x cubed plus 1 squared. Denominator will always be positive. If I pick a value of x greater than the cube root of 2, something like, for instance, 10, 100, 1000, be obnoxious with those numbers if it's easier to do the work, then this derivative is definitely negative. So when x is greater than the cube root of 3 over 2, I think I did not say the cube root of 3 over 2 earlier. The cube root of 3 over 2, then the derivative of x is less than 0, which would mean the function is decreasing. So you can show that condition of the alternating series test either way that we just talked about. Find a derivative, go through all of your Unit 5 stuff, or set up this inequality and manipulate it algebraically until you get a statement at the end that you can definitely say is true for values of n greater than 1, greater than 2, greater than something small. Second test is the ratio test. Ratio test, even when we have all of them, is always my favorite one. I think it is kind of the easiest one to work with, maybe the most fun to work with algebraically. But a ratio test looks like this. We have a series, our series from n equals 1 to infinity of a sub n. And then we're going to find the limit as n approaches infinity of a sub n plus 1 over a sub n. So the ratio of a term and its preceding term. And then that's going to equal some number. We have one condition, 3 stages for this. If L is less than 1, then our series converges. If L is greater than 1, our series diverges. And if L equals 1, we have no conclusion. In this particular case here, that would mean that we need to go try another test. If all that we're really working on for a non-alternating series is the ratio test, we don't have other tests, this should kind of cease to be a giant problem. So an example of a ratio test looks something like this. If we have a series from n equals 1 to infinity of something like 6 to the n over n factorial, the ratio test is excellent for exponential expressions and factorial expressions. If you see some kind of expression where you have that variable exponent or that changing exponent and or factorials, ratio test is excellent. So as we go through this, what we're going to do is find the limit as n approaches infinity of 6 to the n plus 1 over n plus 1 factorial divided by 6 to the n over n factorial. And we want the absolute value of all of that. Be careful with that absolute value. I often forget that when I'm doing this work. Be careful that you don't forget that. And here we have a complex fraction. So it is easier to right away turn this into a multiplication problem with the reciprocal of your denominator. So that would look like the limit as n approaches infinity of 6 to the n plus 1 over n plus 1 factorial times n factorial over 6 to the n, and keep those absolute values. Now when you're looking at this, you have expressions that look similar. I would recommend that you just move them around so that we can do some algebraic simplification pretty nicely here. Sorry. Okay, that is not what I want to be doing. Sorry. Okay, so limit as n approaches infinity. Here we have 6 to the n plus 1 over 6 to the n. We can write this as 6 to the n times 6. And then we see that our 6 to the n's cancel. So I have 6. And then I have n factorial over n plus 1 factorial. N factorial meaning n times n minus 1 times n minus 2 times n minus 3. N plus 1 factorial meaning n plus 1 times n minus 1, and so on and so on and so on. Or in other words, n plus 1 times n factorial. So again, those n factorials can clear, or they can cancel each other. And I just have n plus 1 as my denominator. with the absolute value. Don't forget your absolute value. So this equals the limit as n approaches infinity of 6. I can even pull the 6 out if I want to, of 1 over n plus 1. The limit as n approaches infinity of 1 over n plus 1. We're back to our horizontal asymptote rules. The comparison of the degrees of the numerator and the denominator will equal 0. So this entire thing equals 0. 6 times 0, 0. That would mean, in this particular case, this series, the series from n equals 1 to infinity of 6 to the n over n factorial, converges because our limit is less than 1. And that's essentially how you use the ratio test. I want to show you one more quick, very quick, hopefully, use of the ratio test just to remind you of some important limit qualities. This is going to look like it's set up almost exactly the same way, but is actually a little bit different here. So we're going to look now at the series n to the n power n over n factorial. So all that I did was change the 6 to an n. Unfortunately, that doesn't mean that I can just take my work from before and change my 6 to an n, because this n will have to become an n plus 1 in my numerator fraction as well. So this becomes the limit as n approaches infinity of n plus 1 to the n plus 1 power over n plus 1 factorial over the original a sub n. I'm going to go ahead and flip that right away and multiply by the reciprocal. So I will have n factorial over n to the n and absolute value bars. So let's start working with this. I'm going to separate my first numerator so that I have n plus 1 to the n power, and then I still have this plus 1, so I just have n plus 1. Over n plus 1 factorial times n factorial over n to the n power. And here, if I look at this combination, n plus 1 times n factorial is n plus 1 factorial. So all three of those expressions cancel. And then I am left with the limit as n approaches infinity of n plus 1 to the n power over n to the n power. And instead of writing this like this, I am going to not do that. I'm going to put all of this in one set of parentheses and take all of that to the n power. And then I'm going to rewrite this one more time. And hopefully we can recognize what's happening here. And when I rewrite like this, we see this formula that we've used a lot, or we've seen a lot in an Algebra 2 or pre-calc world. This looks like our exponential growth formula. This looks like an interest situation where we have a compounding period that is happening indefinitely. So if you can remember what happens when we are compounding interest all the time, we are compounding interest every single possible time period that we can, we use the letter E. This limit here as n approaches infinity, that is what I should actually have just put there. This limit is equal to E. So almost the exact same setup as the problem before, but instead of just 6 to the n, I had n to the n, which changed the work a little bit and led us into a limit situation where we have the limit definition of the letter E. And I just wanted you to recognize that, to either realize that that needs to be something that you review or just something that you already know and recognized easily. Either one, make sure that that limit definition of E is somewhere in your kind of formula bank. And then in that particular case, E is greater than 1, so that series would diverge. And that is the ratio test. Okay, now we're going to add in one more approximation method. So we now have a basic method of approximation using just a tangent line at a point to approximate values of x close to that particular point. We also have Euler's method that we talked about in the beginning of this session of using a tangent line, but adjusting that tangent line every so often. And now we're going to add in a Taylor Polynomial approximation, which will use a power series involving derivatives. And I'm not going to do much more than just give you this formula here and then use it in an AP problem, because deriving it or really talking about its pieces would require learning all about power functions, which we are not talking about. But just know that if we put all of the usual topics back into Unit 10, so not just the 5 particular sections covered this year, we could take ourselves from the idea of convergence and divergence through all of our tests for convergence to ideas like a radius of convergence and a power series, and then very naturally get ourselves here to this Taylor polynomial approximation. But we are just going to dive into what this formula actually tells us. And in this formula, we have this letter A. A is the center, or the value of x that we are centering our Taylor polynomial around, and that will be given to us in a function or in a question. So really what we are doing is we are creating this series where we have various levels of derivatives. So I have a function, its first derivative, its second derivative, its third derivative, and so on. Also, let me add things that are actually important here. And then I have this x minus a, x minus the center to the 0 power to start, and then, nope. And then x minus a to the first power, x minus a to the second power, x minus a to the third power, and so on. And then I also have, to start, 0 factorial as my denominator, and then 1 factorial, 2 factorial, 3 factorial, and so on. So hopefully this is a fairly simple formula to build pattern-wise, even if you don't have all of the background into where it came from. It is incredibly pattern-based, and the terms do step through a fairly natural progression if you see that pattern happening. So we are going to just jump right into using this question so that we can practice that formula. So question number 2 for today, this is 2016 number 6 question. The function f has a Taylor series about x equals 1, there's our value of a, that converges to f of x for all x in the interval of convergence. This interval of convergence, radius of convergence, comes from a section that we are not looking at this year. It is known that f of 1 equals 1, f prime of 1 equals -1/2, and the nth derivative of f at x equals 1 is given above. So that is right here. Write the first 4 non-zero terms and the general term of the Taylor series for f about x equals 1. Okay, so let's just start writing that out first. So f of x equals f of 1 plus f prime of 1 times x minus 1. Again, remember 1 is my a, plus f double prime of 1 times x minus 1 squared, plus f triple prime, or the third derivative, not of 3, I just said third and wrote 3, of 1 times x minus 1 cubed. And then I have my denominators. If you want to write denominators the whole way, you can. 0 factorial, 1 factorial, 2 factorial, 3 factorial. And even if you wanted to really kind of make sure your pattern is the whole way there, you could add in this x minus a to the 0 power as well, so that you can physically see these stepping points of function, first derivative, second derivative, third derivative, 0 power, first power, second power, third power, 0 factorial, first factorial, that is not a thing, 1 factorial, 2 factorial, 3 factorial. Okay, and now we have to do this. Now we have to actually get all of our numbers. And the hard part here, hard is maybe not the best word, the tedious part here is getting these derivative values. And that is why we are generally given something that looks like this. This is how I figure out my derivatives. So let's use this idea here in order to figure out this second derivative and third derivative. The first derivative is already given to us. So if I use this formula, I'm going to write it so that I can bring it down to somewhere that we can work. My n, my value of n here is going to be the derivative number that we're working on. So when we work on now, for example, the second derivative, my n equals 2. So I have -1 squared, 2 minus 1 factorial, 2 squared. That n value is 2. And when I do that, my second derivative evaluated at 1, I will get, what will I get? 1/4. Then I'm going to do that entire thing again when n equals 3. So I have -1 to the third power, 3 minus 1 factorial over 2 cubed. And that will give me a negative number. My -1 is being cubed. And I will have 2 factorial over 8. So I will have -1/4. And that's the real work that you have to do for a Taylor approximation. If you're given just this general term function for your derivatives, you have to step through and actually do all those calculations. Other option is that in the question, just like we're given this first derivative here, we're also given a second derivative, a third derivative, and whatever we actually need. And now we're going to take that and we are going to substitute in all of our numbers. So f of x equals f of 1. This is going to be hard because I'm going to need to zoom in a lot, sorry. F of 1 is equal to 1. We have x minus a to the 0 power, which is not anything, and then 0 factorial. I added this in here because just a quick note, and this happened in the evaluation of a derivative as well. 0 factorial equals 1. It is not 0. Just be careful about that. And then I need my first derivative, which is -1/2. And that is times x minus 1. That denominator of 1 factorial is doing nothing here. Second derivative is 1/4. And then I have a 1/2 because of my 2 factorial. And then x minus 1 squared. And then my third derivative is 1/4. I have a 3 factorial, which is 6. And then x minus 1 cubed. That is the beginning of our question. This right here, first 4 non-zero terms, 1, 2, 3, 4. That non-zero part is included in these questions because it is fairly frequently the case where this first part here is 0, which would mean if we need the first 4 non-zero terms in that particular case, we would have to go up to the 4th derivative term as well. So just be careful if you are doing a Taylor polynomial approximation question. Just saying first 4 non-zero terms does not mean that we're using function, first derivative, second derivative, and third derivative automatically. We have to make sure that none of those terms are 0. Okay, now we also need the general term. So I'm going to take this away so that we can write over here. So our general term is all of this without all of our numbers. So our general term is going to look like this. Okay, our general term, where were we looking? Our general term, we're going to have some derivative at 1 times x minus 1 to that over n factorial. And because we know what this is, so there's our general term. That was, oh, that was not given to us here. That was in the Taylor polynomial approximation formula. So there's our general term, but since we know what this derivative is, we're going to put that into our equation or our expression here. So that again is -1 to the n power n minus 1 factorial over 2 to the n. And when you look at this here, you could leave this. This is fine. This is the actual piece here. This can be simplified if you wanted to, n minus 1 factorial over n factorial. That is just n in your denominator. So we could leave it without the simplifications, or we could simplify this to just n in the denominator. And there's your general term. The next thing that we do for a Taylor approximation is actually use that with some value of x. So second part here, the Taylor series from the part above can be used to represent f of 1.2 as an alternating series. It's an alternating series because of this -1 situation. Notice that we have minus, plus, and so on. Use the first 3 non-zero terms of the alternating series to approximate f of 1.2. So be careful about what it is asking you to do. We just want the first 3 non-zero terms. So let's go back and grab that. That means that I want these 3 terms right here. And all that we are going to have to do when we do this is make this x 1.2, 1.2, 1.2, and we throw that into a calculator and end up with f of 1.2 equaling 0.905 as its approximation using a Taylor series. So once we build the Taylor series using it, nice and simple, we throw in a value for x, throw this in a calculator, and get a value. All right, one quick question. I'm not going to walk the whole way through this, but I do want you to see this connection here. This is a 2012 question. It's number 4 on the 2012 BC exam. And this question connects Euler's method and a Taylor series approximation. So information about a function is given above. We have all of this here. It's also known that f of 1 equals 15 and f double prime, so the second derivative evaluated at 1 equals 20. First part, use Euler's method with 2 steps of equal width, starting at x equals 1, to approximate f of 1.4. That means that we would start with f of 1, use the derivative evaluated at 1, with a step of 0.2 to get us to f of 1.2. And then once we are at f of 1.2, I will use the derivative evaluated at 1.2 with a step of 0.2 to get, I already wrote that, to get to 1.4. And when we do that, f of 1.4 in this case, I want to show you the setup, not necessarily plugging in numbers over and over and over. F of 1.4 is equal to 19. Then, same exact question, we can go through a second part with the Taylor polynomial approximation. So in this one, write a second degree Taylor polynomial for f about x equals 1. Use the Taylor polynomial to approximate f of 1.4. So a second degree Taylor polynomial about, what is my a value, 1, would have f of 1, and then f prime of 1, the first derivative, times x minus 1, plus the second derivative, evaluated at 1, x minus 1 squared over 2 factorial. And when we do that, we can use that for f of 1.4. F of 1.4 would be equal to, in this particular case, not equal to, approximated as 19.8. So they're not incredibly close approximations. Here I have 19, here I have 19.8. But we can see that we can use the 2 different methods of approximation that I talked about in this session in the same question. We really can relate all of these different topics to one question. So this is what we have talked about today. Hopefully you saw in the questions that I chose for today, you really can work through so many different parts of calculus in one free response question, just because we are looking at a differential equations for your response question, for instance, does not mean that differential equations, everything we talked about in the differential equations section, is the only information that you'll use in that question. All of these ideas of calculus really do tie together very well and can all be used together in one question. So this is the end. I'm going to come back to you now. This is the end of our calculus work. We worked through 5 different sessions for just AB material and then 2 for the extra BC material. So if you want to go back and review any of that, the breakdown between the 2 tests, the AB and the BC, looks like that. There are 5 AB sessions that we did on all of our Wednesdays and then 2 BC sessions. Again, if you have any questions, please don't hesitate to reach out via the email address in all of these session slides, classes@prepmatters.com, and I will get you as detailed of an answer as I can as soon as I can. I wish you the best of luck on your calculus exam. I hope you had fun working with us.